Okay, now we have Netanel Davidovich, a senior manager in data science research from DoubleVerify. It's a pleasure to have you here with us today, Netanel, and he will speak about auto-labeling of datasets. Netanel? אני לא בטוחה. תבדוק.
Can you hear me? Okay. This is the clicker here? Oh, but I can, all right. Fine. So hi everyone, and thank you for joining me in this talk about auto-labeling of datasets. My name is Netanel Davidovich, and what we do in DoubleVerify is classify online content and match it to the publishers and advertising agencies that want their ads along the right content. So we need to understand the content, very diverse context deeply. The scale at which we work is 100 million of data points a day, either text, video, audio, and images. And you can see a few samples of the diversity and complexity of the content we are dealing with. There is never enough data, and usually if we label manual data, it's not enough yet. So how can we expand the labeled data on an unlabeled data set and still yield a good result? So this is what we are going to see in this talk. We are going to see automatic labeling using a label spreading, and for it to be reliable enough to build an MVP or a POC, we will use a stratified k-fold approach on a small subset of labeled data. So the initial point is either not enough data or not reliant enough data. We don't want a lot of data because there is diminishing returns, not too much added information. So just to take it from the first part to the second part of not enough to good enough. We will need for this two main components. One is an embedding model based either on our domain or close enough to separate the content well. And we will need unlabeled data set, a big one, to spread the labels on. As you can see at the plot below, in case you have a very bad embedding model, but a lot of good data and diverse data, you will see a bad separation in between the classes, as you can see on the left-hand side. On the right-hand side, you can see undiverse enough data, but good embedding, and that's also not good enough to generalize over the domain. So illustratively, the initial point is a lot of unlabeled data in gray at the top, and your classes labeled overlay on them. And taken from scikit-learn at the plot below, the initial step is the unlabeled data in orange points, and the labeled subset, if you can see, of 2 points in light blue and dark blue. After label spreading, they are separated well based on distance metric. The metric that you choose for the process is highly relevant for the success of the separation for your business. So we recommend you use a business metric or a metric that does correlate with your business as much as possible. So here are two basic snippets. One is the classical label spreading. The second one is the self-training classifier, here shown to be operating with an SVM. The plot on the left is also taken from scikit-learn. On the left-hand side column, you can see the results on label spreading, the classical label spreading. On the right side column, you can see the results of the SVM. Pretty comparable results. On SVM, you will have control over the kernel and because of it on the runtime, if you're using it on a big data set. So this is a diagram to show the process that we are going to do. The initial step is to have at gray the data set, a core set, in this case 2 classes, have it diverse enough, and run label spreading on them. This is the naive result, illustrative here. The dark colored are the naive label spreading result. The slightly brighter color is the threshold optimized per all the label spreading. But we're going to use a stratified k-fold approach in order to optimize and optimize the threshold in order to minimize the bias in the result. Label spreading is very greedy, so this is one way to generalize a hindrance of it. So this is an illustration you can see in white points omitted from a fold in the label spreading. Another fold, a different subset is omitted, and you can get either classified in category and average out the thresholds, or you can majority vote the results in order to have successful auto-labeling, which is not overfitted. The final result, you might find that the threshold for some categories is very different from another, allowing a bigger amount of labeled samples if your threshold is low enough to be optimized on. And if not, the threshold automatically will be much higher, allowing less samples to be categorized for that category. So this is the code snippet that does this. I hope the presentation will be shared. But just in case, this is very naive, stratified k-fold over the process. So the caveats of this method is that the data set bias, the data that you choose to classify on, to spread on, is highly important in this case. You want as diverse as possible of a data set. If the core set is also biased, you might find you're not pushing too much new information into your data. You also want to make sure that your embedding space or your embedder is very aligned with your content or your target to solve. And the biggest caveat is that sparsely visual features like in medical imaging, not as Bella showed, but a slightly smaller classification task or slightly smaller features will not be shown in an embedding space unless the embedding space is trained on it. So the takeaways is, if you have a big enough data set but you don't have the amount of budget or resources to manually label it, it's not a dead end. If you have a small set of labeled samples and your data set is not huge, but it's still too big to run a POC on in a small amount of time, this is a good approach, pretty reliable. And the gap that you might breach with this is either time or money or both, basically. So that's it. Thanks, and come say hi.